Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into the outermost reaches of space, to a place both real and imagined, a place called the edge of everything. But don't worry, we're not going anywhere fast. We'll take our time, gently drifting through the stories that brought us here, and the starlight that travelled billions of years just to meet your eyes. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into what NASA saw at the edge of everything together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. You see, when we speak of edges, we usually think of something sharp, a ledge, a cliff, a line drawn with finality. But the universe doesn't work that way. It doesn't end in a fence or a curtain. It doesn't say, beyond here there be dragons, and yet there is still an edge, a place where our tools, our telescopes, our most delicate machines have looked outward and said, that's as far as we can see. But seeing is not the same as understanding. Sometimes, the farther we look, the more we find reflections of ourselves, questions, longings, and the silent echo of curiosity. The edge of everything isn't just about galaxies and black holes. It's about wonder itself, what we choose to reach for even when we know we'll never quite touch it. When the Hubble Space Telescope was pointed at a seemingly empty patch of sky for days on end, what came back was breathtaking. Not a void, but a crowd. Thousands upon thousands of galaxies packed into a single image, no larger than a grain of sand held at arm's length. And with the James Webb Space Telescope, we've looked even deeper, not just into space, but into time itself. What NASA saw wasn't an edge in the usual sense. It was a beginning, one unfolding at the limits of light, age, and imagination. And then, there are the Voyagers, tiny emissaries, drifting farther than anything we've ever built. Beyond the pull of planets, beyond the sun's protective breath, they are still whispering back to us, from a place where starlight is thin and silence reigns. But tonight isn't about answers. It's about the soft hush of perspective, about standing at the shoreline of everything, with our toes in the cosmic surf, listening. Listening for what's out there, yes, but also for what's within. Because sometimes the edge of everything is not out beyond the stars, but in that quiet space inside you, the place where awe lives, where sleep tiptoes in, and where questions gently glow without needing to be solved. So breathe easy, settle in, let's float together now, toward the first of many edges. So, what exactly is the edge of the universe? It's a gentle kind of paradox, because in the same breath that we say the universe has no edge, we also say it has an edge we can't see beyond. That might sound like a contradiction, but in the vast, stretchy logic of space, it makes perfect sense. You see, when astronomers speak of the edge, they don't mean a wall or a border, they mean a limit, not of the universe itself, but of what we can observe, a horizon. Just like standing on a calm ocean shore, you can see only as far as light travels, and no farther. In our case, the ocean is the universe. And the light? It's been travelling to us for a very, very long time. Light moves fast, about 300,000 kilometres every second. But the universe is old, about 13.8 billion years old to be exact. So, if something sent out a beam of light 13.8 billion years ago, and that light has just arrived now, that object sits at what we call the observable edge. But here's the twist. Because the universe has been expanding all this time, that object isn't 13.8 billion light-years away anymore. No, it's now much farther, more like 46.5 billion light-years. This is what we mean when we say the observable universe. It's everything we can currently see, because light has had time to reach us, even if the thing that sent the light is now much farther away. So in a strange way, looking out into space is like looking back in time. The farther we gaze, the older the light, and the farther we go, the less we see. Not because space ends, but because light simply hasn't had enough time to reach us yet. It's like looking down a long hallway with the lights turned off at the far end. The hallway might continue forever, or it might stop, but we can't know, not because there's a wall, but because our flashlight only reaches so far. Astronomers call this invisible boundary the cosmic light horizon. Beyond it, we believe there's more universe, possibly much more, maybe infinite, but we'll never know for sure, not unless the laws of physics change, or unless time itself decides to give us a little more of it. And so, when NASA points its telescopes into the deepest, darkest patches of sky, it's not searching for an ending, it's searching for beginnings, for the first galaxies, the first stars, the earliest light that broke through the fog of creation and whispered, "I was here." There's something poetic in that, isn't there? That our limit, our edge, isn't a barrier of stone or silence, but a horizon of light and time. And even though we can't cross it, we can lean toward it, reach toward it, with eyes and instruments, with data and dreams, and we have. Again and again, we've aimed our lenses and detectors at the farthest corners we can find, not to find where things stop, but to find where they start, because the edge is where beginnings live. And if that feels a little bit like looking into a memory that isn't yours, that's because it is. A memory the universe kept safe, in photons that have travelled across eternity just to reach you. Let's drift now into one of the quietest, most profound experiments ever done in space, one that began not with fanfare, but with a question so simple, it sounded almost foolish. What happens if we point the Hubble Space Telescope at nothing? Not a galaxy, not a planet, not even a twinkle, just a seemingly empty patch of sky, no bigger than a grain of sand held at arm's length. That was the idea in 1995, when a small team of astronomers decided to risk precious telescope time to stare without blinking at what appeared to be a vacant void in the constellation Ursa Major. For 10 straight days, Hubble stayed focused on this nothingness, and when the images were collected, processed and layered together, the result was astonishing. That nothing wasn't nothing at all, it was filled, not with stars from our own galaxy, but with galaxies, entire galaxies, each one a swirling system of billions of stars, spirals and ellipses, disks and irregular blobs, thousands of them just floating there, quiet, distant, ancient, and all of them packed into that tiny, sand-grain-sized sliver of sky. It was called the Hubble Deep Field, and it changed how we think about the universe. Because if that one small spot contained thousands of galaxies, then the whole sky, when fully surveyed, must hold hundreds of billions, and maybe more. Galaxies upon galaxies, layered like whispers upon wind, fading into red and shadow. What Hubble revealed wasn't just more stars. It revealed depth. Not the depth of space as distance, but as time. The deeper the image, the older the light. Some of the galaxies captured in that image had sent their glow out across the universe when Earth was still molten and empty. When there were no oceans, no mountains, no eyes to ever see them, until now. Later versions of the project, like the Hubble Ultra Deep Field, pushed even further, using longer exposures, more sensitive sensors, and a quiet kind of patience. One image alone captured light from galaxies that existed just 600 million years after the Big Bang. Tiny sparks in the newborn universe, huddled together like campfires in the void. And yet, despite the wonder of it all, there's something strangely soothing in the idea that the universe was never truly empty. Even when we thought we saw a blank canvas, there was structure, pattern, presence, waiting patiently for us to notice. Perhaps it's a reminder that emptiness is often just an illusion, that when we take the time to look, really look, we find things we couldn't have imagined. That's what NASA saw, not an edge, but a layer, not silence, but ancient music, played in wavelengths too slow for ears, too old for memory, but just right for light. And the sky? It was never blank, just waiting. Now let's drift a little deeper, into a place where even starlight begins to stretch and glow and finally fade into heat. If Hubble was a pioneer of visible light showing us the stars and galaxies in rich colour and fine detail, then the James Webb Space Telescope, or JWST, is a whisperer of ancient warmth. It doesn't look at stars the way we do. It listens for infrared light, the long stretched waves of energy that even Hubble couldn't hear. And it listens very, very carefully. Launched on Christmas Day in 2021, Webb unfolded itself like a golden origami flower 1 million miles from Earth. There, in the cold quiet of space, it nestled into a spot called Lagrange Point 2, where the pull of Earth and the Sun cancel just enough to let it float in stable balance. Shielded from sunlight by a 5-layered sail no thicker than a fingernail, JWST began to look, backward in time and outward in space. What it saw took even scientists by surprise. galaxies that shouldn't have been there, stars that seemed too bright, too formed, too early. One image, a deep field of its own, showed dozens of galaxies with light from over 13.3 billion years ago, light that left its source when the universe was barely a toddler. In some cases, these were not gentle spirals or familiar ovals. They were chaotic, compact, bursting with newborn stars. It was like stepping into a nursery and finding the children already building cities. You might wonder, how can JWST see farther than Hubble? How can it see what's hidden? The answer lies in the stretching of light. As the universe expands, the light from distant galaxies is pulled along with it, like taffy. What began as visible light is stretched into infrared, growing redder and redder until it disappears from ordinary sight. That's where Webb comes in. It was designed not to fight this stretching, but to embrace it, to follow the glow into the invisible, into the gentle warmth of time itself. Imagine light like a wave on a pond. If Hubble listens for ripples, JWST listens for the slow, rolling swells that only come from far, far away. And in that slow surf of ancient energy, it has found galaxies we didn't expect, some that challenge our models, some that shimmer like distant lanterns on the first night of the universe. Even stars themselves, some of the very first, may be within reach soon. Not yet, but soon. The cosmic dawn is no longer just a theory, it's a place we're starting to see. And maybe that's the most wondrous part, that we live in a moment where we can build something delicate and golden, send it 1,000,000 miles away, and let it look back, not at us, but at before us, before Earth, before the sun, before almost everything. No. And yet, that light still arrives, softly, faithfully, like a memory too old to belong to us, but somehow still ours. Let's sit with something curious for a while, something that at first feels like a trick of words, but soon settles into a truth so vast it reshapes how you think about everything. In space, distance is time. Not just metaphorically, not just poetically, but literally. When we measure how far away a star or a galaxy is, we don't just say kilometers or miles, we say light years. And every light year is both a measure of distance and a measure of how long ago. Because nothing moves faster than light, not even the thoughts you're having now. So when you look up at the stars, you're not seeing them as they are, you're seeing them as they were. The moon, about 1¼ seconds ago. The sun, roughly 8 minutes in the past. The nearest star system, Alpha Centauri, over 4 years old by the time its light reaches you. It's a strange kind of time travel, but one you experience every time you look up at the night sky. And the farther we look, the older the light, until we reach galaxies whose light left them billions of years ago. Some from when Earth didn't exist, some from when there weren't even planets yet, just clouds of hydrogen gas folding slowly into the first stars. NASA's telescopes like Hubble and Webb don't just look outward, they look backward. When they capture the faint red shimmer of a galaxy over 13 billion light-years away, they are capturing the past itself, not a painting of it, not a simulation, but the actual light, the actual photons that left those galaxies before our solar system was even dust. There's something profoundly humbling about that, because we often think of history as something we read about in books, but here, in the cosmos, history shines. It travels across unimaginable gulfs of space just to be seen, to remind us that the universe is old, that we are new, and that in looking outward, we are really reaching for something long gone, but still glowing. And yet, there's a catch, a quiet twist that makes everything a little more haunting. Some of those galaxies, those beautiful spirals and glowing knots of starlight, we will never reach, not because we don't know how, but because the universe is expanding, and some parts are moving away from us faster than light itself. Not breaking the rules, but bending them. Because it's not the objects that are speeding away, it's space that's stretching. Imagine dots on a balloon. As the balloon inflates, the dots drift apart. Not because they're moving, but because the surface between them is growing. That's what our universe is doing. And some dots are now forever out of reach. So even though we can still see their ancient light, the galaxies themselves are gone from our future, reachable. But rather than sadness, maybe there's comfort in that. That we can know something was here, that it burned bright for a while. And though we'll never touch it, we were touched by it. And in a way, that's what you're doing right now. Sitting here listening, surrounded by darkness that isn't really empty. It's full of light that's been travelling for billions of years, only to arrive in this quiet moment, in this quiet night, in you. In terms now, let's imagine you're holding a magnifying glass, not to read something tiny, but to see something impossibly far away. In space, this isn't just a metaphor, it's real. It's called gravitational lensing, and it's one of the strangest, most beautiful tricks the universe plays with light. It begins with something Einstein predicted long before we could ever observe it. According to his theory of general relativity, gravity doesn't just pull on objects, it bends the very fabric of space and time. And when space is bent, so too is the path that light follows. So if a massive object, like a galaxy or a black hole, sits between us and something even farther away, its gravity warps the light coming from behind it. And that distant light bends around the middle object, like sunlight curving around the edge of a glass. The result? The background object becomes distorted, duplicated, or even magnified into arcs and rings of light. These are known as Einstein rings, and they're not science fiction. They're actual photos, actual images we've taken, many with Hubble and now with JWST, where one galaxy appears wrapped in a halo of another, like a jewel in a crown of warped space-time. What makes gravitational lensing so special is that it lets us see things we shouldn't be able to see. Galaxies too far, too faint, or too obscured by cosmic dust suddenly appear, brought into view by the natural magnifying power of gravity itself. It's like the universe has built its own telescopes, massive clusters of matter that bend space in just the right way, letting us peer deeper into the cosmos than our instruments alone ever could. Sometimes we find entire lensed galaxies whose light has been travelling for over 13 billion years, stretched and curved by everything it passed on the way. And when we study them, carefully untangling the distortions, we glimpse what the universe looked like when it was still a child. In fact, many of the earliest galaxies discovered by the James Webb telescope owe their visibility to this cosmic lensing effect. Without it, they might have stayed hidden forever, buried in the haze of time and distance. And there's something quietly poetic about that gravity, often thought of as a heavy, dragging force, can act instead as a lens, a revealer, a spotlight on the distant past. It reminds us that the universe is layered, that even the things we see clearly may be shaped by invisible hands, forces curving gently around corners of time. And when you look at an image of space and you see something oddly stretched, something looped or smeared into arcs of blue and gold, know that you're not just looking at a trick of light. You're looking through a doorway, a passage cut not by tools, but by mass, by patience, by physics old enough to be cosmic law. And the view? It's not what's right in front of us, it's what lies behind. We spent some time marvelling at what we can see, the galaxies Hubble unveiled, the ancient light JWST captured, the bent rays whispered through gravitational lenses. But now, let's pause and think about the other side of that wonder, the unseen, the places where light hasn't yet arrived, or never will, the parts of the universe that remain dark, not because they're empty, but because they're quiet. Even now, after centuries of stargazing and decades of telescopes in space, we are still mostly blind. In fact, if you think of the universe as a great layered painting, what we've seen so far is only the thinnest top glaze. According to current estimates, everything we've ever observed with any telescope, every star, galaxy, planet, or quasar, makes up just about 5% of the universe. The rest? It's hidden. Dark matter is the first great shadow. We can't see it, we can't touch it, it doesn't emit light or radiation of any kind, but we know it's there. Galaxies spin faster than they should. Clusters hold together more tightly than gravity alone can explain. Something unseen is tugging at the cosmos from the shadows, and we've named that something dark matter. It makes up about 27% of the universe, not just lurking in corners, but woven through everything. An invisible web that shapes the structure of galaxies, clusters, even the great cosmic filaments that stretch across billions of light years. And then there's dark energy, the even more mysterious sibling. It doesn't hold things together, it pushes them apart. We believe it's responsible for the accelerated expansion of the universe, for the growing gaps between galaxies, for a future where more and more of the cosmos slips beyond our sight. Dark energy accounts for about 68% of the universe. It's not something we can bottle or point to. It's not energy in the everyday sense. It's more like a property of space itself, a pressure that deepens as space stretches. So even though our telescopes are more powerful than ever, and our reach has extended to the very edge of the observable universe, most of what is remains hidden. Even the light itself hides sometimes. Cosmic dust, tiny grains scattered between stars and galaxies, can obscure even the brightest signals. Some parts of the sky glow in infrared, but look utterly dark to our eyes. Entire nurseries of stars are tucked inside thick clouds of interstellar dust, their beauty veiled until the right kind of instrument looks their way. And then there are the places beyond the cosmic light horizon. Places so far that their light hasn't reached us yet, and maybe never will. Not because it's not there, but because the universe is expanding too quickly, and the light is still on its long, impossible journey. So as much as we've seen, what we haven't seen is far greater. And maybe that's okay. Maybe it's comforting to know that the cosmos still holds secrets, that there are mysteries we can sit beside without solving, that wonder doesn't require full visibility. Just a little light and a little quiet. Because sometimes the beauty isn't in what we've uncovered, it's in what we still don't know, and what patiently waits behind the curtain of silence. Let's drift now to a quieter corner of our cosmic neighbourhood, a region where sunlight arrives not in golden warmth, but as a faint whisper, a place past Neptune, past the last familiar planets, where icy worlds spin slowly in the dark. This is the Kuiper Belt, a vast ring of frozen remnants, stretching in a loose halo beyond the orbit of Neptune. You might think of it like the attic of the solar system, not abandoned, but hushed, filled with forgotten things, strange shapes, ancient leftovers from the time when everything was just beginning. Pluto lives here. Once called the ninth planet, now officially a dwarf planet, Pluto orbits in a tilted, elongated path, gliding through the Kuiper Belt like a lonely bead on a frayed thread. It's cold here, about minus 230 degrees Celsius, so cold that nitrogen, methane and carbon monoxide, which are gases on Earth, freeze solid into glaciers and plains. But Pluto is not alone. Out here, there are many more worlds, some even bigger. Eris, for example, is just slightly smaller than Pluto, but more massive. It's so far away that a single orbit around the Sun takes 557 Earth years. Haumea, shaped like a spinning football, rotates so fast its middle bulges outward. And Makemake, a reddish sphere with an icy surface, might have once had an atmosphere that froze and fell like snow. They all belong to a strange, shimmering category we call trans-Neptunian objects, or TNOs, bodies that live in the outer regions beyond Neptune. Many of them reside in the Kuiper Belt, which stretches from about 30 to 50 astronomical units from the Sun. That's 30 to 50 times farther than Earth's orbit. But even beyond that lies the scattered disk. This is where orbits become wild, slung at sharp angles, flung outward by Neptune's gravity long ago. The scattered disk is home to objects that don't follow neat paths. They come close, swing far, dip above and below the plane of the planets. They are wanderers, messengers from a time when the solar system was young and chaotic. The things out here are not easy to find. They don't shine. They don't reflect much sunlight. Some are so small or so distant that we only know they exist when they briefly pass in front of a background star, like a shadow on a dark wall. Others, we find, by watching their faint, slow drift across the sky over many nights. Still, we've catalogued hundreds, and we suspect there may be tens of thousands, maybe more. And what's remarkable is this: these icy, distant bodies aren't just frozen rocks, they are time capsules, leftovers from the early solar system, barely changed since the beginning. While planets have collided, shifted and grown warm, these small worlds have remained in the deep freeze, unchanged, untouched, waiting for light, waiting to be seen, waiting to tell the story of how it all began. And so, we drift here now, not for spectacle, but for stillness. Because in this twilight realm, where the sun is just another bright star and silence has a texture, we're reminded that edges are not always endings. Sometimes they're storage. Sometimes they're memory. And sometimes they're beginnings we forgot we still had, far beyond the Kuiper Belt, beyond even the scattered disks' erratic dancers. There are objects whose orbits seem too strange, too distant, to fully explain. They reside in a realm that's not quite mapped, not quite named, a region so remote that the sun looks like a bright pinhole. And in this far silence wander a few icy enigmas. One of them is called Sedna. Discovered in 2003, Sedna is a reddish frozen world about 1,000 kilometers across. It's not a dwarf planet like Pluto, not quite, but it might be one day. What makes Sedna remarkable isn't its size, or its surface, or even its isolation. It's how it moves. Sedna follows an orbit so stretched that it takes over 11,000 years to go around the Sun. For comparison, humans first developed written language only about 5,000 years ago. That means Sedna hasn't completed a full orbit since before the end of the last ice age. It's currently on its long, inward journey, moving closer, but only slightly. Its farthest point from the Sun, or aphelion, lies about 940 astronomical units away. That's 940 times farther than Earth. No known planet flung it there. No comet acts that way. It seems misplaced, like a page from another book tucked into the middle of ours. And Sedna isn't alone. In 2018, astronomers found something even farther. A pale dot moving slowly across the night sky. So faint, it could have been a glitch, but it was real. They named it 2018 VG18 and nicknamed it Far Out. At the time of its discovery, Far Out was orbiting at about 120 agenometals, farther than any known object in the solar system. Later, another object was found even farther, unofficially called Far Far Out, estimated to be orbiting well past 130 agenometals. These bodies are so remote, their orbits so wide and tilted, that scientists began to wonder, what could be influencing them? Enter the mystery of Planet 9. According to some models, the way these distant objects cluster, how their orbits tilt in similar ways, suggests that a large unseen brown dwarf, but something in between. Maybe 5 to 10 times Earth's mass, hiding in the cold shadows beyond Pluto, too faint to see. No one's found it yet. But the math suggests something is there, something shaping the orbits of these quiet Voyagers at the edge. And so the search continues, not just with telescopes, but with algorithms, simulations, patient scans of the deep sky. And maybe one day we'll find it. Or maybe we won't. But in the meantime, Sedna and Far Out drift on, not asking to be understood, just moving, slowly, patiently. Like ancient punctuation marks in a sentence we haven't finished reading. They are part of the solar system, but only barely. They belong to the Sun, but not in the way Earth or Mars does. They orbit, but their loops are more like long sighs stretched across the centuries. And maybe that's what makes them beautiful. They remind us that not everything in our celestial neighbourhood is neat or close or familiar. Some parts are strange, unsettled, quiet in a way that feels ancient. And out there, at the edges where gravity still whispers and darkness deepens, we are reminded the story isn't done. There are still blank pages ahead, still footsteps in the dark we haven't yet followed. Now, let's turn our gaze not to icy worlds or forgotten objects, but to something human, something small, made of wires and panels and hopes, something we built with our hands and sent into the dark to keep going long after we could follow. Their names are Voyager 1 and Voyager 2, twin spacecraft launched in 1977, designed to explore the outer planets. But their journey didn't end with their primary mission. They just kept going. And in doing so, they became something more than probes. They became messengers. When they lifted off, disco still filled dance floors. The Berlin Wall still stood. The internet hadn't been born, and yet both Voyagers are still flying, nearly half a century later, quiet, steady, and alone. They've passed the gas giants. They've slipped beyond the gravitational leash of the planets. They now travel through the outermost fringes of our solar system, through a realm so still it almost doesn't feel real. Voyager 2 was the first to launch, but it took the longer route, a grand tour of Jupiter, Saturn, Uranus, and Neptune. It sent back breathtaking images: Jupiter's roiling storms, Saturn's icy rings, Uranus's sideways spin, and Neptune's deep blue mystery. Each flyby was like a silent dance, graceful, distant, profound. Voyager 1, launched shortly after, took a faster path and focused on Jupiter and Saturn before breaking away on a direct route outward. It passed Saturn in 1980 and never looked back. In 1990, just before it shut off its cameras to conserve power, Voyager 1 turned around one last time. At the request of Carl Sagan, it looked homeward and captured an image now famous as the pale blue dot. Earth, from nearly 6 billion kilometers away, appeared as a tiny speck suspended in a shaft of sunlight. No continents visible, no borders, just a delicate pixel of blue floating in the void. That image changed how we think about ourselves, and while Voyager 1 carried that memory, it kept moving. In 2012, it became the first human-made object to enter interstellar space, to cross the invisible border where the sun's influence fades and the space between stars begins. Voyager 2 followed in 2018, entering that same boundless region from a different angle. Even now, both spacecraft continue to send back data, low bandwidth whispers of particle density, magnetic field strength, plasma waves. It's not much, just a stream of numbers from the edge. But it's something, and it reminds us that, while our feet are on Earth, a part of us is out there, carried forward by curiosity and engineering and the quiet will to go on. They move at about 17 kilometers per second, which seems fast until you realize how far there still is to go. At that speed, it will take Voyager 1 over 40,000 years to pass near another star, and even then, it won't come close, just a polite drift through the outskirts. But that's okay, because the point was never to arrive, the point was to go, to stretch a hand into the dark and let it float, to say, we were here, and mean it. And now, drifting between stars, powered by the fading warmth of plutonium, each Voyager continues on its way, not lost, just free. And in a way, maybe that's the most human thing we've ever done. Now, let's pause at a place where something subtle happens. Not a crash, not a line you can see, but a boundary nonetheless, a real one. Not drawn in ink, but in plasma, in particles, in the whisper of solar breath, finally giving way to the chill of interstellar space. This place is called the heliopause. It's not a fence, not a shell, more like the edge of a breeze, the point where the wind from our sun, the solar wind, slows down, weakens, and is finally overtaken by the pressure of the space beyond. The solar wind is a stream of charged particles that flows outward from the sun in all directions. It travels for billions of kilometers, creating a vast bubble around the solar system known as the heliosphere. Inside this bubble, the sun's influence is strong. Its magnetic field threads through the wind like a net, shaping the behavior of particles and plasma. But, like all breaths, it doesn't go on forever. At a certain distance, the solar wind slows from supersonic to subsonic. This point is called the termination shock. And farther still, where the solar wind and the interstellar medium reach an uneasy balance, that's the heliopause, the outermost edge, the place where the solar system, in a physical sense, ends. Voyager 1 crossed this boundary in August of 2012. Voyager 2 followed in November of 2018. How did we know? Not with photographs, not with blinking lights or warning signs, but with a sudden change in plasma density. Inside the heliosphere, the solar wind is low density and fast moving. But just beyond, in interstellar space, the plasma is thicker. Still faint by Earth standards, but measurable. When Voyager passed the heliopause, the instruments registered this subtle shift. The wind from the sun faded. The magnetic field changed. The environment quieted into something colder, darker, and older. And yet, even there, the influence of the sun is not completely gone. Its light still shines, though dimly. Its gravity still holds on, ever so gently. But its breath no longer reaches. In a way, the heliopause is like the hush before a forest. You leave the clearing. The birdsong fades. The wind moves differently. You've entered a new place, not hostile, but unfamiliar, not dangerous, but different. Scientists believe the heliosphere helps protect us from high-energy cosmic rays that flow between the stars. Like a shield, it softens the blow of particles from beyond. But outside the heliopause, that protection falls away. Voyager now feels the full texture of interstellar space. Thin and quiet, but ancient and vast. What lies beyond is not empty, just sparse, full of drifting atoms, slow-moving fields, energy too weak to sense but too real to ignore. And this invisible line, the heliopause, is something no human had ever crossed until our little machines did. It was never meant to be a destination. No plaque, no ceremony, just a slow, steady crossing into the unfamiliar. And maybe that's why it matters so much. Because this is the true physical edge of our home. Not a planet, not a moon, but a threshold, where the sun's breath ends and the galaxy begins. So, what does space sound like when you're past the planets? Past Pluto, past the Kuiper Belt, past even the soft edge of the sun's breath? What does Voyager hear out in the dark? The answer is simple and strange and beautiful in its own quiet way. Mostly, it hears nothing. Not the kind of nothing that comes with silence on Earth. A room with the fan turned off, or a hilltop when the wind stops. No, this is a deeper silence. A silence made not by absence but by emptiness. A place where particles drift light years apart, and where every signal takes hours just to arrive. And yet, there is something. When Voyager 1 crossed into interstellar space, its plasma wave instrument began to pick up faint vibrations, tiny oscillations in the density of space. Supernovae, distant black holes, and all the things exploding in the universe. Inside the heliosphere, these rays are partially blocked, but beyond the heliopause, the curtain lifts, and suddenly Voyager is exposed to the full chorus of the galaxy. Tiny, powerful particles zipping by at nearly the speed of light. It also feels changes in the magnetic field, not dramatic twists or reversals, but slow, subtle shifts. Out here, the sun's magnetic grip has loosened. What remains is the galactic field, a background hum of magnetism from the stars and gas that fill the Milky Way. And then, there's the data that Voyager doesn't send. No images, no colour, no sweeping panoramas of space. Its cameras were turned off long ago to conserve energy, to protect its systems, and perhaps because there's nothing to see. No planets to photograph, no moons casting shadows, just the dark between stars. It sends us measurements, numbers, streams of ones and zeros, but those numbers tell a story, a slow increase in plasma density, a sudden drop in solar particles, a spike in cosmic radiation, a world beyond worlds. It's not a loud story, not dramatic, but it's steady. And in that steadiness is something profound, because for the first time in history, something made by human hands has stepped beyond our home. Not to plant a flag, not to gather souvenirs, but simply to go, to drift, to listen. And that little machine, no bigger than a small car, is still doing its job, decades after it launched, billions of kilometers away, powered by the quiet decay of radioactive fuel whispering back to us across the dark. It's a reminder that space isn't just about what's visible, it's about what's measurable, what's felt, what patiently reveals itself in the numbers. And sometimes those numbers are the lullaby, the rhythm of silence, the proof that something still moves, even here. Before the Voyagers left home, before they passed Jupiter and Saturn, before they touched the edge of the sun's breath and drifted into interstellar space, something quiet and extraordinary was tucked inside each of them. Something not designed to gather data or take pictures or send measurements. It was a gift and a message, meant for no one in particular, and maybe for everyone. It's called the Golden Record. Each Voyager spacecraft carries one, a gold-plated copper disc, about the size of a vinyl LP, etched with care, sealed for endurance, and encoded with the essence of who we are, or at least, who we were, in 1977. The record contains music, greetings in 55 languages, the sounds of wind and rain, a heartbeat, a mother kissing her child, laughter. It holds images of Earth, mathematical diagrams and chemical formulas, photographs of people eating, dancing, learning, farming. The double he Willie Johnson. From traditional Peruvian flute to a Japanese shakuhachi piece. A tiny curated concert drifting through space. All of it preserved in analog grooves, encoded instructions and a hopeful gold sheen. It's not likely anyone will ever find it. The odds are laughably small. The galaxy is vast, the distance is impossible. Even in 10 million years, the Voyagers will still be sailing through the quiet, with no destination, no ears to listen. But that was never the point. The Golden Record isn't really about reaching someone else. It's about reaching outward, about choosing to tell our story, even when we don't know if anyone is listening, about recording the heartbeat of a planet and placing it in a bottle, casting it into the ocean of stars, and saying, softly, "Here, this was us." It's hope pressed into metal, curiosity made tangible, and perhaps more than any other object we've sent into space, it shows the strange, luminous contradiction at the heart of being human. We are small, but we reach. We live on a pale blue dot, orbiting a medium-sized star, in a quiet corner of a galaxy among billions, and yet, we send messages into the void. Not to be heard, but to be true. As Carl Sagan once said, the spacecraft will be encountered, and the record played, only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. So now, the Voyagers sail on, their instruments aging, their power slowly fading. But the golden records remain, untouched, unscathed, protected against the silence of space and time. And even if no one ever finds them, they are still out there, carrying a kiss, a greeting, a heartbeat, a song, and maybe that's enough. Let's pull back now, farther than we've pulled before, farther than stars, than galaxies, than clusters of galaxies. Imagine, if you can, zooming out until even spirals like the Milky Way begin to look like specks, dust on a darkened window. Out here, space begins to show its grandest structure, not in the arrangement of planets or stars, but in the scaffolding of everything. And what we find is surprising. The universe, at the largest scales, looks like it has a texture, a pattern, a structure too vast to see without backing away for billions of light years. Astronomers call this the cosmic web. It's a delicate, interconnected network of filaments, vast strands of galaxies woven together like silk. Between these strands lie voids, immense empty regions, some hundreds of millions of light years across, where galaxies are few and far between. Imagine bubbles nestled together, with galaxies clinging to the walls between them. It looks almost organic, almost alive. This wasn't always what we expected for a long time. we assumed the universe would be uniform at the largest scales, a smooth sea of stars, evenly distributed like sugar in water. But observations slowly revealed otherwise. Galaxies tend to gather, clusters form, superclusters stretch like bridges, linking cosmic islands across unimaginable distances. Gravity, gentle and patient, is the artist here. Over billions of years it pulls matter together, a whisper here, a tug there, guiding galaxies into strands, strands into walls, and between them the emptiness blooms. If you could travel along one of these filaments, you'd pass through cluster after cluster, suns, planets, maybe civilizations, then drift into a great silence, a void, and then after millions of light years, into another bridge of light. These structures have names. The Great Wall, discovered in the 1980s, stretches over 500 million light years. The Bhuta's Void, by contrast, is a near-empty sphere over 300 million light years wide. It's like a honeycomb made of galaxies and space, or a sponge soaked in gravity and time, and it's still growing. The universe expands, and with it, this great web continues to stretch, gently, silently, like bread rising in the oven of cosmic time. What's most humbling, perhaps, is realizing that our own galaxy is just one glowing dot in one strand, in one corner of one wall, in a structure so vast that no human could ever cross it. Not in a lifetime, not in 1,000, not in all of recorded history combined. But still, we see it. We trace its outlines through surveys and telescopes, map it with data and colour-coded charts, and give it names that sound poetic and strange: filaments, voids, clusters, walls, and somehow, knowing this doesn't make the universe feel colder or more distant. It makes it feel connected. That even in the silence there is shape, even in the void there is pattern, even in the darkness a gentle hand has woven something breathtaking, something enormous, something slow, and something beautiful. This peasantition to describe daily falls on the state, this reading on the mints of the Blanc and Chloe Rembers, and send the similar parter, the parents in the Corone, the bignesses and the cland. The breck this meaning reasons, then death, they min trying to map the night sky, not just the stars you can see with your eyes, but all the galaxies, clusters and strange flickers hidden across billions of light years. Not just a chart of constellations, but a full three-dimensional atlas of the cosmos. That's exactly what the Sloan Digital Sky Survey, or SDSS, set out to do. Beginning in the year 2000, this ambitious project used a dedicated telescope in New Mexico to scan the heavens, night after night, year after year. Not to gaze, but to catalogue, carefully, systematically, pixel by pixel. What emerged from that effort is one of the most profound portraits of the universe we've ever made. The Sloan survey didn't just take pictures, it gathered spectra, the light fingerprints of distant galaxies. With each scan, it measured redshift, the stretching of light caused by the expansion of the universe. And from that redshift, astronomers could estimate how far away each galaxy was and how fast it was moving. Now, imagine plotting every single one of those galaxies on a map. What you get isn't a flat page, it's more like a deep sea of luminous dots, arranged in wisps and arcs and foamy branches. A spiderweb of light, a structure so vast that no computer screen can show it all at once without shrinking the galaxies into specks. In one famous image, a wedge-shaped slice of the universe, you can see this structure clearly. It's like looking into a glowing tunnel made of galaxies. Dense regions form clusters, long strings become filaments, and in between lie vast voids, places where almost nothing exists at all. It's mesmerizing, not because it's noisy, but because it's so orderly. Galaxies aren't thrown about at random. They gather, they stretch, they arrange themselves according to the subtle push and pull of gravity across time. From the chaos of the early universe, a pattern emerged, not because someone planned it, but because nature, given enough time, tends to sculpt something elegant. And the Sloan survey didn't stop with galaxies. It mapped quasars too, brilliant ancient beacons powered by supermassive black holes. It recorded stars within our own galaxy, nebulae, asteroids, and even the faint flickers of distant supernovae. It became one of the most cited and influential datasets in the history of astronomy. But perhaps the most beautiful thing it gave us wasn't a number, it was a feeling, a sense of scale, of pattern, of quiet awe. Because when you look at those Sloan maps, at the thin threads of galaxies curling through space, you realize you're seeing the architecture of the cosmos, not a random scatter, but a structure, a rhythm, like veins beneath skin or frost on glass. And somewhere, in one of those filaments, our galaxy sits, a small swirl of stars, spinning quietly, held in place by gravity, surrounded by neighbours we may never meet, but at least we can see the pattern, at least we know we're part of it. Now let's lean into the patterns a little more, into the swirls and folds of this cosmic web, and ask, where exactly do we belong in all of this? The answer is surprisingly comforting. Our galaxy, the Milky Way, is not drifting alone in space. It's part of a group, a small collection of galaxies known as the Local Group, which includes Andromeda, the Triangulum Galaxy, and dozens of smaller companions. But even that's just a speck in something far more immense. We now know that the Local Group is itself part of a vast continental-scale structure called the Laniakea supercluster. In Hawaiian, Laniakea means immense heaven, and it fits. This supercluster is not a simple blob of stars. It's a flowing region of space, about 520 million light-years wide, containing over 100,000 galaxies. It includes familiar clusters like Virgo and Hydra, woven together into a sprawling landscape where galaxies move not randomly, but like rivers drawn downhill. And what's even more remarkable is how we found Laniakea. Astronomers didn't just count galaxies, they traced their motions. By measuring tiny velocity shifts, they realized that galaxies aren't drifting aimlessly. They're flowing, being drawn toward dense centers of gravity along the filaments of the cosmic web. That's when scientists noticed something strange. The galaxies around us are not just pulled by local gravity, but by something larger, farther, and not yet fully understood. They called it the Great Attractor. It's a region in the direction of the Centaurus constellation where galaxies, including our own, appear to be moving toward. It lies about 250 million light-years away, but the view is partially obscured by our own Milky Way, hidden behind a curtain of dust and stars. And yet we feel it. Its gravitational pull, its quiet invitation. We don't know exactly what it is. It might be a concentration of galaxies and dark matter hidden behind our galactic plane. Or it might be something we haven't yet learned how to see. But the idea itself, that the Milky Way is falling gently along invisible slopes of space, makes the universe feel less still and more alive, less like a frozen map and more like a slow, eternal dance. And just beyond the Great Attractor is something even larger, the Shapley supercluster, a gravitational heavyweight even more massive, stretching the map of motion farther still. It's like discovering that the whole neighborhood is flowing towards something, and we're floating along with it. And all around, between these massive regions, lie boundaries, places where the motion slows, where galaxies are sparse, cosmic coastlines, if you like. They don't separate nations or languages, but gravitational territories, subtle regions where motion changes, where one river of galaxies fades into another. So in this grand ballet of matter, we're not lost. We're moving, slowly, gracefully, carried by invisible tides across distances we can barely imagine. And as we drift, we learn, not just what's out there, but where we belong. As we drift deeper into the fabric of the universe, there are places where the pattern falters, where the smooth web of galaxies ripples in ways we didn't expect, where light carries whispers that don't quite match the song we thought it was singing. One of the most famous of these whispers is called the cold spot. It's a large region of the cosmic microwave background, or CMB, that appears slightly cooler than the rest of the sky. Not cold in the way you might feel temperature, of course. The entire CMB is already just a few degrees above absolute zero, but colder in comparison. A faint dip, a subtle asymmetry. This cold spot stretches over a region of space hundreds of millions of light-years across, and it doesn't seem to fit the statistical bumps and wiggles we expect from the early universe. According to the models, such a low-temperature patch shouldn't really be there, at least not at that size. So what could it be? Some scientists think it might be the result of a supervoid, a massive, underdense region that the CMB photons pass through on their way to us. As the light crosses this emptier space, it can lose a bit of energy, a process known as the integrated Sachs-Wolf effect. But the effect is small. Too small, some argue, to fully explain the anomaly, and that leaves the door cracked open to other possibilities, to questions that echo beyond the edge of what we know. Some have wondered if the cold spot could be evidence of something even more exotic. Perhaps a bruise from another universe, a place where our own universe may have bumped against another bubble in a multiverse, a faint collision in the cosmic womb. Of course, we don't know. The data is murky. The interpretation is delicate. But the cold spot remains peculiar, a thumbprint on the oldest light we can see. And it's not alone. Another strange phenomenon, entirely different but equally baffling, is something called dark flow. In the late 2000s, scientists studying galaxy clusters noticed a curious thing. Some of them appeared to be moving in the same direction, at high speed, toward a point far beyond the observable universe. This wasn't a small drift. It was a coherent motion, as if vast stretches of space, spanning hundreds of millions of light years, were being gently pulled or pushed by something invisible. What could cause that? One theory suggests it might be an artifact, an illusion in the data. Another proposes that it could be the gravitational tug of massive structures outside our observable universe, places we'll never see, but which might still be shaping what we can. Or, more radically, it could be a hint that our universe is part of something larger, that space itself might have structure beyond its edge. And every so often, that larger structure tugs at the fabric of our reality, just enough for us to feel the ripple. Again, we don't know. These mysteries lie at the fringe of what's measurable. But their existence reminds us that the universe is not yet fully tamed. There are places where the data doesn't settle, where the map smudges, where the song skips. And those places, those cold spots, those flows, those silences, are not flaws. They're invitations to wonder, to look again, to ask questions we don't yet know how to answer. Because even now, after all the mapping, all the scanning, all the careful mathematics, there are still places where the universe softly says, "You don't know everything yet." Before there were galaxies, before stars, before even atoms could form, there was light. But not the kind that sparkles or dances or flickers on walls. This light was everywhere, soft, even, uniform, a glow that filled the entire universe, and then, slowly, faded. What remains of that glow is called the cosmic microwave background, or CMB, and it is the oldest light we can see, not because it's ancient in a mythic sense, but because it literally comes from about 380,000 years after the Big Bang. Before that time, the cosmos was filled with a hot, dense fog of particles, free electrons and protons scattering light like mist in a crowded room. Nothing could travel far. Photons bounced endlessly, unable to escape. But then the universe cooled. Electrons settled down, protons found their partners, atoms formed, and suddenly, for the first time, light could move freely. It decoupled from matter and began to travel, in every direction, unimpeded. That moment, when light broke free, is what we now observe as the cosmic microwave background, the afterglow of creation, a perfect whisper from the edge of visibility. We didn't see it until the 20th century. In 1964, two radio engineers, Arno Penzias and Robert Wilson, were calibrating a large antenna when they stumbled upon a faint, persistent hiss. It was everywhere, no matter where they pointed, and no matter what they tried, they couldn't make it go away. What they'd discovered, by accident, was the remnant glow of the early universe. Later missions refined this view. In the 1990s, COBE, the Cosmic Background Explorer, confirmed the smoothness of the CMB and found the first tiny fluctuations, subtle ripples that hinted at future galaxies. Then came WMAP in the 2000s, giving us a more detailed map. And finally, Planck in 2013 gave us our most precise image of the CMB, like a baby photo of the cosmos, taken when it was just a few 100,000 years old. What do we see in that image? A soft map of colour-coded temperature fluctuations. Tiny differences, mere millionths of a degree, spread across the sky. These fluctuations are important. They are the seeds from which all structure would eventually grow. Every cluster of galaxies, every star, every planet, all of it began as a slightly warmer or denser patch, in this ancient glow. And the light? It's not white or golden or blue. It's microwaves, long, invisible waves stretched by the expansion of the universe. If we could see it with our eyes, the whole sky would gently glow with heat from the past. Not bright, but steady. Not loud, but constant. The CMB isn't just a leftover, it's a boundary, the farthest we can see. Beyond it, everything is still hidden, not because it doesn't exist, but because light hasn't reached us yet from earlier times. And so, when we gaze at this ancient radiation, we are truly looking at a wall of light, the last scattering surface, as physicists call it, not a wall to stop us, but a veil, a shimmering horizon between what we can measure and what came before. In its faint, static whisper, the CMB tells us that the universe was once young, that it was hot and dense and filled with potential, and that everything we know, everything we are, grew from its soft, flickering pattern. A lullaby, still playing, billions of years later. Microwave background has just been released. The universe is no longer an opaque fog. Light can travel freely. But still, the cosmos is dark. Because even though the universe is now transparent, it doesn't yet shine. There are no stars, no galaxies, no glowing gas clouds or spiraling arms, just neutral hydrogen atoms drifting through the ever-expanding darkness, calm, cool, and waiting. This era is called the Cosmic Dark Ages, and they lasted for hundreds of millions of years. But, slowly, invisibly, something began to stir. Tiny fluctuations in density, those barely there ripples in the early universe, began to pull matter together. Gravity, quiet and relentless, gathered hydrogen into clumps. The clumps grew dense, warmed, collapsed, and somewhere, in that vast, lightless sea, the first stars were born. They were nothing like our sun. These were population 3 stars, massive, bright, short-lived and made entirely of hydrogen and helium. They burned hot and fast, flooding the universe with ultraviolet light, and that light changed everything. As the UV radiation spread out, it began to ionize the surrounding hydrogen, breaking it back into free electrons and protons. The fog that had once settled into calm atoms was now being reversed, reheated, re-energized. This period, when the first stars and galaxies relit the universe, is known as the Epoch of Reionization. It's a beautiful name, one that sounds like sunrise. And in a way, that's exactly what it was. The first cosmic dawn. The light broke through the darkness, not all at once, but in patches. Each star, each young galaxy, carved out glowing bubbles in the hydrogen sea. Those bubbles expanded, overlapped, connected, until the entire universe was once again filled with charged particles and starlight. And only then did the universe truly begin to look like it does today. Galaxies formed, clusters gathered, the cosmic web began to shine. What was once invisible now glowed. And we're only just beginning to see it. Because this era, this moment of first light, is one of the hardest to observe. The light is ancient, redshifted beyond the visible, obscured by distance and cosmic dust. But telescopes like JWST are finally peeking into this forgotten age. With its infrared vision, JWST can see further than Hubble ever could, capturing galaxies that formed only a few 100 million years after the Big Bang. Faint, red, ancient. Some of them are so massive and bright that their very existence challenges our models, galaxies that shouldn't have had time to grow so quickly. And yet, there they are. It's like watching the universe blink open its eyes. And all of this, the dark ages, the first stars, the ionized bubbles, the spreading light, reminds us that transparent foundations were laid, and when the light returned, it did not just fill the sky, it revealed the sky. And that sky has never stopped glowing since. Let's pause for a moment. Right here, at the edge of everything we've seen, the maps, the stars, the filaments, the echoes. We've traced the contours of galaxies, followed the soft glow of the beginning, listened to the silence of intergalactic space. But now comes a question that feels both childlike and impossibly large. What shape is the universe? It's easy to imagine it like a sphere, a snow globe perhaps with galaxies swirling inside, or maybe a flat sheet, stretching out forever like a cosmic pancake, or something else entirely, something curved or twisted, something we don't have words for. And the truth is, the answer is complicated. Not because we haven't looked, but because what we're trying to measure is everything. Scientists have tried to answer this using the only tools we have: light, geometry, and the distant whispers of the cosmic microwave background. If the universe were curved, like the surface of a ball, light beams would eventually meet again. If it were saddle-shaped, curved in the opposite way, they'd diverge forever. And if it were flat, they'd travel in straight lines, side by side, endlessly. And so, by studying the patterns in the oldest light, the tiny temperature fluctuations in the CMB, astronomers have measured the angles of those ancient photons. And what they've found is surprising in its simplicity. The universe appears to be flat. Not flat like a sheet of paper, but flat in terms of geometry. Parallel lines stay parallel, triangles add up to 180 degrees. Space, it seems, follows the familiar rules, even on the grandest scales we can test. But here's the twist. Even in a flat universe, space can still be finite. Just like the surface of a cylinder or a torus, a donut shape, it can loop back on itself without having a visible edge. You could travel in one direction forever and eventually return to where you began without ever hitting a wall. In that case, the universe would be finite but unbounded. No edges, no borders, just endless continuity. A cosmic echo chamber with no end in sight, but we don't know for sure. There could be folds we haven't detected, loops too large to measure, twists in dimensions beyond our comprehension. And yet, even with all this uncertainty, there's something strangely comforting about it. That we can ask such a question at all, that we can look at the night sky, stretch our minds across billions of light years, and wonder not just what's in the universe, but what it is. Some theories go further, that space might be just one layer, that higher dimensions, folded beyond sight, could shape the universe's geometry in ways we've only glimpsed through math. String theory, brains, holographic principles, all fascinating, all mysterious, but here, in the quiet, we can let those ideas float. We don't need to solve them tonight, we just need to know they're being asked. That someone, somewhere, is still trying to unfold the shape of everything. And maybe, just maybe, the universe is like a song that never ends. A loop without a chorus, a spiral without a centre, a road without a final stop. Not because it's incomplete, but because it was never meant to be bounded. It was meant to be wandered, to be wondered at. And that's exactly what we're doing, with every map, every telescope, every question asked softly beneath the stars. Infinity. It's a word you've probably heard 1,000 times. It shows up in poems, in math classes, in daydreams. It sounds vast, almost magical. But what is it really? When we talk about infinity in everyday life, we often mean something very big. A sky full of stars, a hallway of mirrors, a number too large to count. Something that stretches on, past our ability to grasp. But in mathematics, infinity isn't just big. It's a concept. It doesn't have a fixed value. It isn't a number in the usual sense. It's a symbol, an idea, a placeholder for the endless. You can't reach it, only approach it. You can divide numbers forever. You can count without stopping. You can zoom into a fractal endlessly, and it keeps revealing more detail. That's mathematical infinity. A tool, a pattern, a kind of poetic boundary. But does it exist, physically? That's where things get tricky. In the real universe, there are limits. There's only so much energy, so much space, so much time behind us and ahead. We can write equations that point toward infinity, but that doesn't mean the universe follows them all the way. Think of a black hole. In theory, its core, its singularity, has infinite density. But no one knows what really happens there. Our physics breaks down. The numbers spin out of control, as if reality itself hits a wall made of infinities. They may not be destinations, but rather signs that our map is incomplete. And then there's the question of space itself. Is the universe infinite in size? It might be. If it's truly flat, geometrically speaking, and continues without curvature, then it could go on forever. No wall, no edge, just more. But it also might be curved back on itself, like the surface of a sphere. In that case, it could be finite in volume, but still have no boundary. You could travel in one direction forever and never hit a wall, only return to where you started, eventually. That kind of infinity is soft, gentle, curved. Not a cliff, but a loop. There's also another kind of infinity to think about. Potential infinity. This isn't something that exists all at once, but something that can keep going indefinitely. Like counting. You never finish, but you're never holding all the numbers at once either. The universe might not be infinite now, but it may keep expanding forever, becoming more and more vast with each passing epoch. And here's where infinity becomes most useful. Not as a description, but as an invitation to keep thinking, to keep asking. It reminds us that our minds can stretch, that our models can reach toward truths even when our measurements cannot. That even if the universe is not literally infinite, our curiosity might be. And maybe that's the quiet magic of infinity. Not that it goes on forever, but that we do. In thought, in wonder, in the steady unfolding of understanding. Because sometimes the idea of something that never ends can bring a strange kind of peace. Let's return to something that may seem simple, but isn't. Something so quiet you don't feel it. Something so vast you don't see it. And yet it's happening all around you, every second of every day. The universe is expanding. This doesn't mean galaxies are flying through space like shrapnel from an explosion. It means that space itself is stretching, like dough rising in an oven, or dots on the surface of a balloon inflating from within. It all started with a discovery in the 1920s, when Edwin Hubble looked at distant galaxies and noticed something strange. Their light was shifted toward the red end of the spectrum. This is called redshift, and it happens when objects move away from us. The more distant the galaxy, the more stretched out its light became. And from that stretching, we learned something profound. Galaxies aren't just moving away from us, everything is moving away from everything else. There's no center, no explosion point, just expansion everywhere, all at once. This revelation gave birth to modern cosmology. It told us that the universe had a beginning, and that it's been growing ever since. But what's actually expanding? It's not the galaxies themselves, they stay the same size. It's not time, it's not energy, it's space. Imagine placing raisins in dough. As the dough rises, the raisins get farther apart, not because they're moving, but because the space between them is growing. That's what's happening to galaxies. The light they emit travels through this expanding space, and as it does, it stretches, its wavelengths lengthen. That's what we see as redshift. This relationship between distance and redshift gave rise to something called the Hubble constant, a number that describes how fast the universe is expanding. For every megaparsec, about 3.26 million light-years of distance, galaxies appear to recede faster in proportion. But even that number isn't fixed. We've learned that the expansion isn't slowing down, it's speeding up. This was one of the biggest surprises in modern science. In the late 1990s, like gravity or magnetism, it's a property of space itself. As more space forms, more dark energy seems to arise, and that energy pushes space to expand even faster, a feedback loop of cosmic proportions. And so, the universe stretches, quietly, relentlessly. From your perspective, it might seem like everything is drifting away from you. But if you lived in a distant galaxy, you'd see the same thing. Because in an expanding universe, every point is moving away from every other point. It's not that we're at the center, it's that there is no center. There's just growth, silent, gentle, woven into the fabric of space itself. And maybe that's what makes the expansion so strange to think about. It isn't loud or dramatic. It's not a wind you can feel. It's not even something you could detect on a human scale. But it's real. It shapes galaxies. It shapes time. It shapes what we can see and what we never will. And it reminds us that the universe doesn't need to be full of noise, to be full of movement. Sometimes, everything can change while you sit perfectly still. Imagine a beam of light, pure and patient, leaving a distant galaxy. It begins its journey across space, gliding silently through the darkness, passing nebulae and star clusters, moving always forward, always toward us. Now imagine that, despite all its steadiness, it will never reach us. Not because it's too weak, not because it's blocked, but because space itself is expanding too fast. This is one of the strangest, quietest truths about our universe. Some galaxies, though they exist right now, are already forever unreachable. This isn't science fiction. It's not a paradox or a thought experiment. It's a measurable reality, a consequence of cosmic acceleration. You see, as we discussed earlier, the universe is expanding, and not just expanding, but accelerating in its expansion, driven by that mysterious dark energy. The farther away a galaxy is, the faster it appears to be moving away from us. There comes a point, about 16 billion light-years from Earth, where galaxies are receding faster than light can travel toward us. That boundary is called the cosmic event horizon. It's not the same as the edge of the observable universe. The observable universe is about 46 billion light-years in radius. The distance light has already travelled to reach us since the Big Bang. But the event horizon is different. It's the limit beyond which light emitted now will never reach us, no matter how long we wait. And that means some galaxies we see today, faint smudges from long ago, are already slipping beyond our cosmic grasp. Their light will continue to arrive for a while, like echoes, like postcards mailed before departure. But no new light from them will ever reach us again. In time, their signals will fade. They will grow redder, dimmer, and eventually vanish. Distance too far. It's a strange thing to be surrounded by stars we'll never meet, to know that the universe, vast and glowing, is slowly closing in on itself, not through contraction but through separation. And in the far, far future, billions or trillions of years from now, distant galaxies will fade from the skies of whatever civilizations remain. Their telescopes will see only the nearby stars. The great cosmic web will dissolve from view, and yet we see it now. Right now. We are living in a privileged sliver of cosmic time. A moment when light from across the universe still graces our skies. When we can study distant galaxies, glimpse the echoes of the Big Bang, and watch the great expansion unfold in real time. And maybe that's a gentle reminder that the night sky is not just beautiful, it is fleeting. Each photon that reaches us has crossed vast space, dodged dust clouds, outlasted stars, and survived billions of years of change, just to land softly on a telescope mirror, or on the back of your eye, or on a camera chip in a silent dome under the stars. And the ones that won't make it? They're still out there, still trying, still moving. And even if we never meet their source again, they remind us of something deep and quiet, that light has a journey, and that journey, even when incomplete, is still full of meaning. So far, we've travelled outward, farther and farther, until we reach the edge of the observable universe. About 46 billion light-years in every direction, a spherical horizon not made of walls but of time. That's how far light has been able to travel since the beginning. But once we arrive there at that soft, glowing edge, a question quietly forms. What's beyond it? It's not an edge in the way cliffs are edges. There's no sign saying, here the universe ends. In fact, most scientists believe the universe continues beyond what we can see, quietly, invisibly, patiently expanding in every direction. The observable universe is just the part of the cosmos whose light has had time to reach us. Beyond that, there could be more galaxies, more stars, more structure, repeating in ways we recognize or diverging in ways we don't. But some theories go even further. They suggest that what lies beyond our observable bubble might not be more of the same universe. It might be a different universe altogether. This is where the idea of the multiverse comes in. It sounds like science fiction, alternate dimensions, other realities, parallel Earths. But in physics, the concept arises not from fantasy but from mathematics, from inflationary theory, from quantum mechanics, from the attempt to explain why our universe is the way it is, and why it could have been otherwise. One idea is called eternal inflation. In this model, the universe didn't stop inflating after the Big Bang. Instead, inflation continues in some regions, bubbling out new universes like foam on the surface of a rising loaf. Each bubble forms its own cosmos with its own physical laws, its own constants, maybe even its own dimensions. Our universe would be just one bubble among many, floating in a cosmic sea we can't see, expanding, colliding, moving beyond our ability to observe. And perhaps, long ago, our bubble collided with another, leaving a scar in the cosmic microwave background, a subtle cold spot, a bruise in the light. That's one hypothesis anyway. Another version of the multiverse comes from quantum mechanics, the idea that every decision, every particle interaction splits the universe into branches, infinite outcomes, infinite timelines unfolding side by side. And yet, even with all these possibilities, there is no clear evidence. No telescope has spotted a bubble universe. No probe has travelled beyond our cosmic horizon. These are mathematical maybes, speculative maps drawn at the edges of what we can know. But that doesn't make them meaningless. Sometimes the questions themselves are the reward. They stretch our imagination, they remind us that even after all the models, all the equations, all the charts of galaxies and atoms and light, we're still just beginning to understand what reality might be. Beyond the observable may lie more stars, or stranger laws, or silence, or nothing. And maybe we'll never know. But we look anyway. We ask anyway because there's something deeply human in that moment, standing at the edge of what can be seen and still wondering what lies just beyond the dark. And maybe that wondering is its own kind of light. It's a natural question, a child's question, a question that seems so simple it must have an answer. Where is the centre of the universe? And if we're not at it, what is? But like so many things in cosmology, the answer is quietly strange. Not because it's complex, but because it gently asks us to let go of how we think space should behave. You might imagine the Big Bang as an explosion, something bursting outward from a central point into empty space like fireworks against a black sky. And in that picture, there would be a centre, an origin point, a place from which everything flew. But that's not what the Big Bang was. It didn't happen in space. It was the beginning of space itself. Space didn't explode into a pre-existing void. The void didn't come first. The void came with the bang. So when we say the universe is expanding, we don't mean that galaxies are rushing away from some hidden centre. We mean that every point in space is moving away from every other point, all at once, equally. In that sense, everywhere is the centre, and nowhere is. To help visualize this, scientists often use the balloon analogy. Imagine a balloon with tiny dots on its surface. As the balloon inflates, each dot moves away from every other dot. No dot is special. No dot is the center of the surface. In fact, from the perspective of the dots, which live only on the surface, there is no center. The center lies in a higher dimension, inaccessible from within. Our universe might be like that. A three-dimensional surface, expanding in a space we can't access or even imagine. Or it might not. The analogy is imperfect, but it helps us let go of the idea that there must be a middle. This is also why redshift doesn't prove we're at the centre of the cosmos. Yes, distant galaxies are moving away from us, but if you lived in one of those galaxies, you'd see the same thing. Galaxies around you would be receding in all directions just as they do from Earth. It's not that we're special, it's that space itself is stretching uniformly. There's no edge, no outer rim, and no privileged position from which the rest unfurls. It's a bit unsettling at first. We like to locate things, to point and say that's where it began. But in cosmology the answer is softer, less certain, and maybe more beautiful, because it means you are at the centre of the universe, and so is everyone else, every point, every observer, every patch of sky. In an expanding universe with no boundaries, the centre is not a location, it's a perspective. A gentle reminder that the universe doesn't radiate from some distant core. It radiates from wherever you stand, wherever you look. And maybe that's what makes it feel so intimate, even when it's so vast. Because when you gaze at the stars and feel very small, you can also remember you are exactly where the story unfolds, not at the edge, not off to the side, but in a place that, like all places, is perfectly central to everything. It's tempting to think of the universe like a container, a box, a snow globe, a thing that floats inside something else. After all, most things we know do have outsides. Rooms have walls, planets have surfaces, balloons expand into the air around them. So surely the universe, vast as it is, must be expanding into something, right? But here's the quietly astonishing truth. The universe doesn't need an outside, and perhaps it doesn't have one. When we say space is expanding, we're not saying it's pushing into a larger void. We're saying that space itself is growing. The distance between things is increasing. Not because they're flying through a larger space, but because the space between them is unfolding. Think of the balloon analogy again, only this time, pay attention to the surface. The dots live on the balloon. As it inflates, they grow farther apart, but they don't move outward into the room. From their perspective, there is no outside. They're not inside anything. They're just the house. But the universe isn't in something else. It is everything. And asking what's outside the universe is like asking what's north of the North Pole. You can take steps in that direction, but eventually there's no more north to go. This doesn't mean there's a brick wall. It doesn't mean you fall off the edge. It means that the concept of outside simply doesn't apply. Some theories, like higher dimensional space or brain cosmology, suggest there might be more beyond what we call our universe. That space-time could be just one layer in a higher dimensional landscape. But even these are guesses, beautiful, mathematical, still unproven. In the language of physics, we say the universe is self-contained. Its shape and structure don't require it to sit inside anything else. And yet, even without an outside, the universe still has boundaries. But these aren't borders you can touch. They're limits to what we can know, or see, or reach. The cosmic horizon, the end of light's journey, the edge of meaning, not of matter. And maybe that's the real magic. Not that there's something on the other side, but that the universe is complete within itself, that space doesn't need a backdrop, that existence doesn't need a stage. It just is, growing, changing, unfolding from every point at once. And somehow that idea, so strange, so quiet, feels comforting, because it means we're not locked in a box. We're part of something boundless, but whole, something that contains everything, not in its walls, but in its being. And maybe there's a kind of peace in knowing there's nowhere else we need to be. Here we are, at the edge, not just of the universe, but of understanding itself. We've followed galaxies to their limits, walked along filaments of light, peered into cold spots and event horizons. We've stretched our minds across expanding space and curled time around corners we can barely see. And yet, there is still more we don't know than we do. There are questions that linger like distant stars, faint, unresolved, beautiful. What came before the Big Bang? What is dark matter? Why does the universe even exist? Questions that science is still working on. Questions that philosophy has asked for thousands of years. It's easy to think of science and philosophy as opposites, one dealing with facts, the other with thoughts. But really, they're companions. Science begins with curiosity, and curiosity is a deeply philosophical act. To wonder, to not know and want to know, to reach into the dark with no guarantee of answers. That's what built the telescopes. That's what launched the Voyagers. That's what etched the golden record with greetings and laughter and music for ears that may never exist. It's not just knowledge we seek, it's connection to the stars, to each other, to the mystery that surrounds us. That's something to rest in. Because science isn't about having all the answers, it's about learning to live with the questions, to measure what we can, to guess where we must, and to admit, gently, that some things may always remain just out of reach. But maybe that's a gift. If the universe gave us every answer, we might stop listening, stop exploring, stop wondering. And wondering is what keeps us awake under the stars. It's what makes a quiet walk at night feel infinite, what turns a flickering light in the sky into a story, a puzzle, a poem. You don't need to solve the universe to feel at home in it. You don't need to grasp every theory or master every law. Sometimes it's enough to sit in the quiet and marvel that there's anything here at all. Science gives us tools, philosophy gives us meaning, and together they whisper something soft and enduring. It's okay not to know. It's okay to ask. It's okay to wonder and not have an answer yet. That longing, the gentle ache to understand, isn't a flaw. It's a sign you're part of this strange, expanding story. You are made of stars, held in gravity, cradled in questions, and in that space between what is known and what is imagined, you can find a quiet kind of joy, a peace that doesn't come from certainty, but from curiosity. It's easy to forget, sometimes, that we've never been to the stars. We haven't walked on Saturn's rings, or floated through the nebulae, or touched the soft dust of distant exoplanets. We've never stood beside a black hole or watched a galaxy turn from just above its rim, and yet we see them, clearly, softly, sometimes even beautifully. Because we've learned how to detect the far away, how to build instruments that let our senses reach across space. And it all begins with light, but not just the light our eyes can see. The visible spectrum, the reds and blues and golden whites, is only a tiny sliver of what's really out there. The universe glows in many languages. Some of them we can't feel. Some we're only just learning to translate. There's radio light, long and slow, like the deep breath of a sleeping planet. There's infrared light, the warmth of dust clouds and distant atmospheres. There's ultraviolet, X-rays and gamma rays, which come from violent, high-energy places, where stars collapse or matter spirals toward annihilation. Each part of the electromagnetic spectrum offers a different view of reality, and over the last century, we've slowly built machines that can listen to them all. Radio telescopes, like the massive dish at Arecibo or the delicate arms of the Very Large Array in New Mexico, detect the sky's deepest murmurs. They trace hydrogen clouds between galaxies and reveal spinning neutron stars, pulsars ticking like lighthouses in the dark. Infrared telescopes peer through cosmic dust. Things that seem hidden to visible light telescopes suddenly bloom into view. Stars being born, planets forming, entire galaxies glowing softly with heat. X-ray telescopes like Chandra reveal the universe at its most extreme. Black holes feeding, galaxies colliding, matter heated to millions of degrees. These are the cataclysms we cannot survive, but we can watch safely from far away. And gamma-ray detectors, like those on NASA's Fermi Space Telescope, capture the brief, violent bursts of dying stars and mysterious phenomena still not fully understood. Each wavelength tells a different story. And when we gather them all together, the universe begins to come into focus. But seeing from Earth has its limits. Our planet's atmosphere, protective and precious as it is, also blocks much of the incoming light. Infrared is absorbed by water vapor. X-rays and gamma rays never make it through. That's why we build telescopes in space. Delicate instruments placed far above the clouds, floating in cold silence. The Hubble Space Telescope, orbiting Earth since 1990, gave us breathtaking views in visible and ultraviolet light. Spitzer, now retired, explored the sky in infrared. Chandra, still going strong, maps the X-ray cosmos. And now we have the James Webb Space Telescope, a marvel of engineering tuned for deep infrared. It sees the faint heat of galaxies from the early universe, their glow stretched and reddened by time and expansion. Each telescope is a kind of eye, not our own, but made with our hands, our minds, our longing. They don't just show us where stars are, they show us how stars are born, how galaxies spin, how black holes bend space, and how light, simple, ancient light, can cross the vastest distances and still reach us. And so, even though we cannot go there, we learn to listen, to look, to build tools that stretch our senses across silence, because we may never walk among the stars, but we are learning to see them in every way the universe allows. For all the light we've captured, all the distant stars we've charted, and all the galaxies we've mapped across the sky, the truth is, we haven't gone very far. Not physically, not with our own hands, our own feet, our own machines. We are still tethered gently, stubbornly, to home. But that doesn't mean we haven't reached. It doesn't mean we haven't tried. In 1969, 2 humans stepped onto the surface of the moon, just 384,000 kilometers away. Not even far enough to qualify as leaving Earth's neighborhood, but far enough to change how we see ourselves forever. They left boot prints in the dust and brought back pieces of another world. They raised a flag in silence, and above them, floating in the black, was Earth, small, fragile, whole. Since then, no one has gone farther, but our robots have. We've sent landers to Mars like Spirit, Opportunity, Curiosity, and Perseverance, each one more capable than the last, each one slowly exploring dusty hills and riverbeds frozen in time. We've studied its weather, scanned its rocks, and even flown a tiny helicopter in its thin, pink sky. We've orbited Venus, braved the storms of Jupiter, and skimmed the icy moons of Saturn. We've seen geysers of water erupt from Enceladus. We've marvelled at the swirling hexagon at Saturn's pole. We've followed the complex rhythms of Jupiter's radiation and watched as Europa's icy surface hinted at oceans hidden below. Then came New Horizons, a small spacecraft with a big dream. In 2015, it passed within 12,500 kilometres of Pluto, capturing images more detailed than anything we'd ever imagined. Before that moment, Pluto was a blurry smudge. After, it was a real place, with mountains, plains, and a heart-shaped patch of frozen nitrogen. New Horizons didn't stop there. It continued on, speeding into the Kuiper Belt, and in 2019 flew past Arakoth, a snowman-shaped object billions of kilometres from Earth, a place no one had ever seen, a relic from the beginning of the solar system. And again we got pictures, stories, data, beauty. And then, there are the Voyagers. Launched in 1977, Voyager 1 and Voyager 2 have travelled farther than any other human-made objects. They've passed Jupiter, Saturn, Uranus, and Neptune. They've sent back shimmering images of planets bathed in sunlight, and carved out maps of magnetic fields and radiation belts. And then, they kept going. Today, both spacecraft have crossed the heliopause, the boundary where the solar wind fades and the interstellar medium begins. They are, in every sense, outside the solar system. And they're still sending signals. Faint, slow, but real. They carry with them golden records, etched with music, greetings, and sounds from Earth. Not because we expect anyone to find them, but because it felt important to say, we were here, we tried. But even these greatest travellers have barely scratched the surface. Space is unimaginably vast. If Voyager 1 were heading toward the nearest star, Proxima Centauri, it would take over 70,000 years to arrive. At its current speed, it would need 1,000 human lifetimes just to visit our closest neighbour. That's the scale we're up against. And yet, we reach. Not to conquer, but to understand. Not because we can go everywhere, but because going even a little is still a miracle. And for every footprint in moon dust, every rover wheel on Martian soil, every faint ping from the dark, we remind ourselves, we are small, but we are not still. Number 117. Somewhere out there, a telescope floats in darkness, silent, golden, and unfolding like a flower toward the deep. The James Webb Space Telescope, or JWST, isn't orbiting Earth. It's much farther, parked at a spot called Lagrange Point 2, or L2 for short, about 1.5 million kilometers from home. That distance was no accident. Gravitational sea, where instruments can rest in cool, quiet stillness. And stillness matters. Because Webb is not just any telescope. It is a heat-sensitive marvel, tuned to detect infrared light, the long, stretched-out glow of distant galaxies, early stars, and exoplanets cloaked in dust. To see that light, it must stay cold, very cold. Its instruments operate just a few degrees above absolute zero. That's why JWST carries a vast sun shield, the size of a tennis court, made of 5 delicate layers of reflective material. The shield blocks the light and heat of the sun, Earth and Moon, all at once, creating a temperature difference across the telescope of more than 300 degrees Celsius. On one side, hot enough to boil water, on the other, colder than the far reaches of space. And nestled behind that shield, a golden mirror, the largest ever sent to space. Made of beryllium and coated with a whisper-thin layer of gold, it unfolds like origami into a 6.5-meter wide eye. Too large to launch in one piece, it had to be folded, tucked delicately into its rocket, and then unfurled in space, one piece at a time. That unfolding wasn't guaranteed to succeed. It took weeks, careful choreography, remote commands, hundreds of single points of failure, and yet, it worked, perfectly. Now, JWST peers into time itself, because looking far, in astronomy, means looking back. The light Webb captures began its journey billions of years ago, when the first galaxies were forming, when the cosmos was young and stars were just beginning to weave themselves into the fabric of darkness. It also studies exoplanets, watching as they pass in front of their stars. With subtle, almost invisible dips in light, Webb can read the chemical fingerprints in those atmospheres, searching for water, methane, even carbon-based molecules, clues, hints, whispers of possible life. All of this, from a fragile golden instrument balanced on a gravitational perch, shrouded in silence. It's not loud. It doesn't burn fuel or blaze trails, but it sees, deeper than anything has seen before. And that's the quiet miracle of engineering the edge. We don't have warp drives, we don't have wormholes, but we have mirrors, we have sun shields, we have equations and patience, and the kind of precision that borders on poetry. And with them, we've built a way to watch the oldest starlight arrive. Not with a bang, but with a glimmer. Long star as leaved in a things. Webb doesn't count, cars a lay. Anyone it says, the long shielding the stars, business also. JWST, relief together, trying to show weeks, despite business. Long before telescopes, long before rockets and equations and spectral lines, we looked up at the stars and gave them names. Orion, Andromeda, Venus, the Milky Way. The act of naming is one of the most ancient things we do. It's how we take something vast and untouchable and make it feel a little more familiar, a little more ours, a gesture of closeness, even in the face of distance, and we still do it. Even now, when we discover a distant moon or an exoplanet circling a sun hundreds of light years away. Sometimes the names are technical, alphanumeric designations like HD 209458b or 2014 MU69, but often when the discovery settles in and begins to feel like part of our story, we give it something mythic. We call an icy Kuiper Belt object Haumea, after a Hawaiian goddess of fertility and creation. We name a lonely world on the edge of the solar system Sedna, after the Inuit goddess of the sea. We call a mysterious interstellar visitor Umuamua, meaning scout in Hawaiian. Each name carries more than just sound, it carries memory, culture and story. It turns coordinates into characters, data into poetry. It's not just about classification, it's about connection. And even in the sterile glow of data streams and orbital mechanics, that need for meaning still burns softly. Scientists studying distant objects sometimes speak of them with unexpected affection, like old friends or quiet mysteries. They talk about stars as if they're personalities, about galaxies as if they're landmarks in a long and personal journey. Naming does that. It gives us a thread, something to hold on to as we drift deeper into the unknown. It says, we saw this, we noticed it, and now it has a place in our minds. Even telescopes carry this spirit. We name them Hubble, Spitzer, Chandra, Webb, after those who helped us understand, who helped us look. The names become echoes of human longing and perseverance. They remind us that we don't explore the stars only with machines, but with memory. And every once in a while, a name breaks through into collective imagination. TRAPPIST-1, a system of Earth-sized planets bathed in red light. Proxima b, a neighbour just 4 light-years away. Titan with its methane lakes. Enceladus with its icy geysers. Suddenly, these aren't just objects, they're destinations, places of interest, questions waiting to be asked. Of course, not everything can be wrapped in a name. The cosmos is vast, and many of its corners remain simply numbered, quietly catalogued in long databases. But the ones we name, we invite them into our story. And maybe that's what naming truly is. Not a claim of ownership, but a whisper of recognition. A way of saying, you exist. You matter to us, even from across the dark. When the Kuiper Belt bribes position for Aurelian, if you could pause time right now and glance up at the sky, you might not notice anything unusual. The stars look the same as they did yesterday. The planets follow their ancient, patient paths. The moon still drifts in silence, pulling at tides. But quietly, this is the best moment in history to stargaze. We are living in what many call a golden age of astronomy. Not because the stars are brighter, not because space has changed, but because we have. For most of human history, the sky was a mystery. We saw patterns, stories, gods, omens. We tracked the rising of Sirius and the slow dance of Mars, but we couldn't see the details. We couldn't peel back the veil. Now that veil is lifting. Today we have instruments that gather more light than Galileo ever imagined. Telescopes on mountaintops and floating in space. Interferometers that combine signals from antennas spread across continents. Spectrographs that can measure the breadth of a planet's atmosphere from trillions of kilometers away. And perhaps more importantly, we can share what we see. An image from the James Webb Space Telescope can be downloaded across the globe in moments. Data from Gaia, mapping over 1 billion stars, is available to anyone with curiosity and a keyboard. Students, artists, scientists, dreamers, we all have access to the sky now, in ways that were once impossible. And we're not just looking, we're finding. Thousands of exoplanets, orbiting stars near and far, distant galaxies that formed just after the Big Bang. Waves in space-time, gravitational ripples from black hole collisions, captured by detectors like LIGO and Virgo. We've built surveys that sweep the heavens every night, spotting comets, tracking asteroids, catching the soft flashes of dying stars. The sky has become dynamic, alive with change, and more is coming. New telescopes are rising. The Vera C. Rubin Observatory, designed to scan the entire southern sky every few nights. The Nancy Grace Roman Space Telescope, aimed at answering questions about dark energy and galactic structure. Next-generation arrays that will let us peer even deeper into the radio whispers of the early universe. It's a golden age, not just because of what we know, but because of how much more we can now ask. And maybe that's the most beautiful part. Because with every answer comes more mystery. We solve one puzzle, and 3 more bloom in its place. There's a moment that happens often in astronomy, quiet, sudden, and strange. A scientist, sifting through lines of numbers, stops. Not because something's wrong, but because something is beautiful. A curve on a graph that dances just right. A light echo from a dying star. A galaxy shaped like a question mark, swirling at the edge of a survey map. In that moment, data becomes more than data. It becomes poetry. Not because it rhymes or sings or fits neatly into a sonnet, but because it stirs something. Something deep. Something wordless. You've seen it too, even if you didn't realise it. The pillars of creation, glowing in dust and light. Those towering shapes captured by Hubble and now revealed anew by JWST. The spiral galaxies, delicate and uncoiling like seashells. The colour-mapped clouds of nebulae, painted in hues our eyes can't see without help. These are not paintings. They're measurements. Wavelengths translated into colours, intensities made visible. And yet, they move us. Even the driest plots, a redshift diagram, a transit curve, a spectral line, can feel like verses when you understand what they show. A planet crossing its star, a galaxy pulled by gravity, a whisper of water in alien air. That's what makes astronomy different from many other sciences. It doesn't just study the universe, it listens to it. It watches it unfold. And in doing so, it tells a story, one that spans billions of years, one that isn't finished. Maybe that's why so many astronomers speak like poets, not because they try to, but because they can't help it. Because when you spend your life watching stars being born or dying or vanishing into black holes, you start to feel the rhythm of it, the hush, the hum, and maybe, without realizing it, you begin to carry that rhythm in the way you speak and think and dream. Of course, behind every stunning image is a mountain of code. Behind every coloured nebula is a stack of calibration files and exposure times. It's hard work, it's technical, it's precise, but it's also deeply human, because all that effort, all the wires and mirrors and math, is in service of a very old desire, to look up, to make sense of the sky, to find beauty in the far away. We don't build telescopes just to collect data. We build them because we want to feel something, because the more we know about the stars, the more we see ourselves reflected in them. Not literally, of course, but softly, like a thought you forgot you were thinking. And so a telescope sends down a file. A server processes it, a scientist adjusts the contrast. And somewhere in a quiet room, someone gasps. Because the universe has just sent us a poem. And for a moment, everything feels quiet and full. So now, softly, let's remember where we've been. Not in footsteps, not in kilometres, but in wonder. We began at the edge, not a cliff, but a quiet blur, where the sunlight fades and the solar wind no longer whispers. There, in the twilight of the solar system, we met frozen worlds. Pluto, with its mountains of ice, Eris, Makemake and Haumea, each a speck wrapped in quiet cold. Their orbits curve like forgotten brushstrokes around the sun, sketching loops that take centuries to complete. Farther still, we glimpse the strange dance of Sedna and Farout, their paths so long and distant, we may never see them return. Perhaps, hidden beyond them, a ninth planet drifts in the dark. Too far to glow, but near enough to pull. And then came the travellers. Voyager 1 and Voyager 2, our most distant messengers. Still moving, still singing, still carrying whispers from Earth, music, greetings, a golden hope etched in copper. They crossed the heliopause into the realm between stars, where the sun's influence finally fades and the silence deepens. Beyond them, we turned our eyes to galaxies, those swirling cities of stars that drift through the cosmic web. We traced filaments and clusters, watched voids stretch like hollows in bread, and glimpsed the Laniakea supercluster, the gentle gravity-woven home of our Milky Way. And as we looked farther, we looked earlier, watching light from when the universe was young. We listened to the cosmic microwave background, the echo of creation. We stood with the James Webb Space Telescope at the edge of time, watching ancient galaxies glow red with age, their light stretched thin by distance and the patient pull of expansion. We asked where the centre is, and found that everywhere is. We asked if there's an outside, and found that space contains itself. We explored infinity, not as a destination, but as a direction, and at each step we found not just science, but something more tender. A quiet rhythm, a soft unfolding, a place to rest. We celebrated the tools we've built. Radio telescopes that listen to the breath of stars, infrared eyes that peer through dust, spacecraft that fly, fold, unfold, and wait in cold silence to see what light may come. We named what we found, not to own it, but to remember, to hold it close, even across 1 billion years. And as we reached farther, we also grew still. We let the unknown be unknown. We listened. And we saw that even the most distant data, the light curves and redshifts and spectral maps, can be beautiful, can be poetry. So here you are now, at the close of the journey, still beneath the stars, still gently turning with the earth. And all the vastness we spoke of, the ice, the fire, the dark, the flame, it has all arrived here, to this moment, to you. The edge isn't far away, It's within you, it's everywhere, and it waits, quietly, for sleep. Now, imagine yourself drifting, not flying, not falling, just floating, suspended at the edge of knowing. Still, quiet, weightless. You're not in danger, there is no pull, only space and silence and a strange kind of peace. Because sometimes, not knowing is its own kind of rest. We often treat mystery like something to solve, a puzzle to be completed, a door that must open. But not every question demands an answer. Not every edge is meant to be crossed. Some are meant to be stood beside, to be watched, to be honoured for their depth. The universe is full of these soft thresholds, places where light stops, where gravity bends, where time stretches into something unfamiliar. We see them from afar, with our understand, the more we've come to see just how much lies beyond our reach, beyond our instruments, beyond even our best guesses. Not because we aren't clever, but because the cosmos is vast in a way the mind cannot hold. And somehow, that's comforting. Because if everything could be known, the mystery would be gone, and with it, the quiet joy of simply wondering. There's a kind of softness in accepting the unknown, like the soft dark of a room just before you close your eyes, like the pause in a lullaby, like the moment when the stars begin to appear one by one and you stop trying to count them and just watch. You don't need to explain why the universe expands, or where the edge really is, or what came before the beginning. Not right now. You can let those questions drift. Let them hum gently, like distant music through a closed window. Still there, still beautiful, but not demanding your attention. Because here, at the edge, is not a place of endings. It's a place of quiet. You are not falling. You are floating, held by the very laws of nature that once seemed so cold, but now feel tender. Gravity cradles your body. Light moves past you like breath. The stars do not press, they wait. And in this moment, you are part of it, part of the same mystery you've spent so long trying to see. You do not have to reach, you do not have to explain. You only have to rest. And if your thoughts begin to drift, if they swirl or echo or dissolve, that's okay. That's what edges do. They blur, they soften, they welcome you to sleep. And now, as the stars wheel gently above you, even if the night is hidden by clouds or city lights or closed eyelids, you can know they are still there, still turning, still shining into the dark. You are a part of this too, not separate from the universe, but shaped by it. The atoms in your body were forged in stars. Your breath is the echo of ancient hydrogen. Your thoughts ripple through a brain powered by tiny electrical currents, currents governed by the same physics that guides galaxies. You, lying quietly now, are not outside of space. You are within it, cradled by it, folded into its story. And the edge we've spoken of, so far, so wide, so strange, isn't only out there. It's also inside you, in the pause between breaths, in the quiet between thoughts, in the wondering that doesn't need to be answered. The cosmos isn't asking you to figure it all out. It isn't waiting for conclusions. It just is, and you are too. Tonight, you don't need to carry questions. You don't need to remember redshift or dark flow or Lagrange points. You don't need to reach for distant stars or ancient light. You've already reached. You've already been to the edge. And now, you can let it go. Let it float, gently, beyond something unimaginably vast. But you are also exactly where you belong. Not in the centre, not on the edge, just here. In the hush between stars and stories. Let your body sink into the fabric of night. Let your breath slow, matching the tempo of the sky. Let your eyes close like shutters on a telescope. Not because there is nothing more to see, but because you've already seen enough for now. And the universe will still be there in the morning, still wide, still patient, still quietly unfolding. Good night, traveller. Sleep well.